Welcome back. In the time between measure and analyze, we collected the data according to the data collection plan for vanilla and chocolate cookies. Different from the data collection plan, we had the opportunity to easily collect 100 evaluations for each cookie type, and of course, we took that chance to enlarge our sample. It is always a good idea to first graphically inspect the data. The histogram of the taste ratings of all cookies with the Anderson-Darling test shows that the data are not normally distributed. To check the plausibility of the data, I also look at the minimum and maximum values. They are in the expected range from 1 to 6. The mean is 3.22 and far away from our target of 1.5 for the rating of taste. The time series plot shows for the vanilla cookies a stationary course of events and for the chocolate cookies a shift in the rating of taste from good to bad. This means there is a difference in taste between the two cookie types. But is this difference statistically significant and practically relevant? Before we test the difference, let us first check the process capability of the chocolate cookies. In the introduction, I roughly explained one meaning of Six Sigma as an index of the capability of a process, and I compared a Six Sigma with a Three Sigma capability. The calculation, in fact, is a little bit more complex as introduced. Statistic programs, instead of sigma values, calculate Z-bench values. They are also based on the normal distribution and convert Z values in percentual lead and vice versa. To avoid confusion, I will use the terms Z-bench and sigma levels equivalent, but there is a difference to the simple term sigma that are introduced in the beginning. To make it easy for you, I included the tool process capability, and I will show you how to calculate the process capability with different types of data. If your data are nominally scaled, and if you know the number of units and defects, then you can calculate the yield, the defects per unit, DPU, the defect parts per million, ppm, and the sigma level. Let us try this for the well-known case of 3.4 defects in 1 million units, with one opportunity for a defect per unit. If you calculate the corresponding sigma level with tables of the normal distribution or with Excel functions, a value of 4.5 for the sigma level will result. In the Six Sigma literature, however, a value of 6 sigma is cited. How can this difference be explained? Michael Harry from Motorola repeatedly observed that in long-term studies the processes varied and drifted over time because they had more chances to also include extreme values. Typically, long-term studies have a sigma shift of 1.5 compared to short-term studies. To better compare long-term with short-term studies, they added 1.5 to the long-term sigma level. This is called process sigma. The term for short-term studies is simply called sigma level. If you need to calculate the sigma level for complex products with several different opportunities for a defect, then the index defects per million opportunities is appropriate. If you, for example, assume 100,000 units with 3.4 defects and 10 opportunities for a defect, then you will get the same results as calculated before. Every opportunity is treated as a unit, and the total number of opportunities result from the number of units times the number of opportunities. If in another case your data are given as Z-bench values, the sigma level, then you can convert it into a percentage value. If on the other hand your data are given as percentage values, then you can convert it into a Z-bench value, the sigma level. If at least your data are cardinally scaled and the specification limits are given, then you can calculate the PP-PPK capability index and the corresponding Z-bench values or sigma levels. If you enter the -6 and +6 as specification limits here, a mean of 0 and a standard deviation of 1, then a value of 6 sigma should result. In fact, the sigma level is only 5.89 for the short-term studies and 7.39 results for long-term studies by adding 1.5 standard deviations. All these calculations can give you a first estimation of the capability of your process under different conditions. Let me now show you the calculations of the process capability resulting from a statistic program. I will concentrate on the important results, but I'm sure you will also understand the other information explained under the corresponding numbers. Number 2 shows the actual and the potential process capability related to the customer requirements listed under number 1. It shows that the actual sigma level is 0.01 and the potential sigma level, the best value you could expect under the same conditions without changes, is 0.03. The mean rating for the taste of chocolate cookies is 3.98 and thus very near to the lower specification limit. The corresponding sigma value is very low, and it would become negative if the X-bar for the taste decreases below the specification limit. Number 4, one sample t-test shows that the mean of the rating also significantly differs from the given target value of 1.5 for the taste. Because the rating data are not normal distributed, the statements about process capability should be interpreted with caution. But we are sure that we have to improve at least the taste of the chocolate cookies. The B-model distribution with the two peaks indicates that there were already conditions for a better process capability. The focus is now on the difference of taste between chocolate and vanilla cookies. The first hypothesis states there is a difference in the rating of taste, the Y, between different cookie types, vanilla versus chocolate, the X. To differentiate between the cookie types and to focus on the relevant output with the bigger problem, I choose the two-sample t-test, although not all conditions for this test are fulfilled here. The Wilcoxon-Mann-Whitney test would be more appropriate, but the t-test is quite robust towards violations of conditions. Number 1 shows a significant result with a p-value smaller than 0.001 compared to the significance level of alpha, which is 5%. Number 2 shows the mean for chocolate, which is 3.98, and the mean for vanilla, which is 2.46. The difference between the ratings of the cookie types thus is 1.52. This difference displays the practical relevance of the result. Number 3 shows this difference together with a related confidence interval. Number 4 illustrates both results, the statistical significance and the practical relevance. The H0 states that there is no difference in the ratings and the value for the difference should be 0. The actual difference, however, we measured in the sample was 1.52 grades between vanilla and chocolate. The confidence interval includes values in a range from 1.16 to 1.89 around the measured mean difference of 1.52 in the sample. Thus we expect with a 95% confidence that the mean of the population, the mu, will fall into this interval. The statistical significance results from the fact that the confidence interval does not enclose the difference 0 as postulated in the H0. Thus we reject the H0 and accept the HA. What is about the practical relevance? After you reject the H0, please ask yourself, does this difference have a practical relevance even if you accept the lower value of the confidence interval, the 1.16? In other words, the practical relevance, in this case the discovered difference, informs us about the importance of the discovered effect for the practice, and the statistical significance informs us about the resilience of the effect for the future. We think that the result should have consequences. If we change nothing with a probability of 95%, the chocolate cookies will also in future be rated at least 1.15 grades worse than the vanilla cookies. The focus is now on the negative influences X on the taste of our chocolate cookies Y. The second hypothesis states there is a relationship between the amount of chocolate X and the rating of taste Y. To test the theoretical assumption about the causal determination of the taste of a chocolate cookie by the amount of chocolate in that cookie, I choose the general regression to statistically test this relationship hypothesis. The rank correlation would be more appropriate here for the ordinal scale of the ratings, but the regression analysis can better demonstrate the ideas behind the hypothesis. Number 1 shows again a significant result with a p-value smaller than 0.001 compared to the 5% significance level. Number 2 shows the negative relationship between the amount of chocolate in the cookie X and the rating of taste Y. The more chocolate in a cookie, the lower the grade value, meaning the better the rating. The regression equation expresses this relationship numerically. Number 3 concerns the practical relevance of this relationship. The determination coefficient is with R-square 97% very high. This means, by varying the amount of chocolate within the investigated range, 97% of the variability of taste can be explained. In other words, the rating of taste of a cookie is to 97% determined by the amount of chocolate in that cookie. Does this also have a practical relevance for our bakery? Of course, also this result should have consequences, because now we are able to forecast and steer the rating of taste of our cookies. At least we have to test the third hypothesis to explain why the amount of chocolate in the chocolate cookies varies. The third hypothesis states there is a difference in the weight of chocolate in a cookie, Y, between the conditions the chef eats the already weighed chocolate versus not, the X. As you can see, with this third hypothesis, I want to again differentiate between cookie types to focus on those cookies with a bigger problem. And again, I choose the 2-sample t-test, although again not all conditions for this test are fulfilled here. Number 1 shows a significant result with a p-value smaller than 0.001 compared to the alpha of 5%. Number 2 shows that the mean for taste when our chef ate the chocolate from the weighed portion equals 4.6. In those cases, our chef did not eat the chocolate from the weighed portion, a mean of 1.5 results. The difference between the ratings of these conditions thus is 3.1 and again reflects the practical relevance of the result. Number 3 shows this difference together with a related confidence interval. Number 4 illustrates both results, the statistical significance and the practical relevance. The H0 states that there is no difference in the ratings and thus the value for the difference should be 0. The actual difference we measured in the sample was 3.1 grades between the conditions chef eats chocolate versus eats chocolate not. With a 95% confidence we expect that the mean of the population, the mu, will fall into the interval between 2.75 to 3.45. And again, this confidence interval does not enclose the 0 as postulated in the H0. We thus reject the H0 and accept the HA. After the rejection of the H0, we again ask ourselves, is this difference of 3.1 respective the lower value of the confidence interval, 2.75, high enough that it should lead to consequences in our bakery? And we again think that it should have consequences. Thus, the focus is now on the root causes of eating the already weighed chocolate for chocolate cookies.